Welcome to this video presentation by the postgraduate student whose poster it represents. We will miss the bustling crowds around the posters at the All Energy Conference this year, but we hope you enjoyed this online version that we have created. Before the presentation starts, I would like to acknowledge the support of our generous sponsors. Without this support, the competition could not proceed and the winning entrants would not receive a financial award. Our platinum sponsor is the Victorian Government through the Department of Environment, Land, Water and Planning. Its brands include Victorian Energy Compare, Victorian Energy Saver, Victorian Energy Upgrade Program, Energy Scorecard and Energy for Business. Their contact details are on the slide. Monash University's Monash Energy Institute is one of our silver sponsors. With over 170 staff involved, the Institute has a vision to bring people together to solve global energy problems. The Monash student posters in this competition represent some of that work. Baywa Renewable Energy is another silver sponsor. Baywa develops both wind and solar projects in Australia as part of a global energy portfolio. Baywa staff have also supported our AIE events in the past, including our Young Energy Professionals Speed Networking events. Our final silver sponsor is the University of Melbourne's Melbourne Energy Institute. Many of you will have attended their regular forums that keep the energy community and public up to date on technical and policy energy matters, and the University of Melbourne posters in this competition reflect some of that work. Seed Advisory is our bronze sponsor, and this small but well-recognised energy consultancy covers both the technical and regulatory fields. Seed Advisory has been a regular supporter of the AIE and a presenter at our events. Lastly, we thank All Energy for hosting our live poster events over the last decade, and we look forward to doing this again post-COVID. These last slides show you our poster winners in the last competition. And I now hand you over to the poster presentation. Thank you.
Hello everyone. In this presentation, we'll be looking at highlights of current and future problems associated with photovoltaic recycling and potential resolution using innovative recycling process such as FRELP. Since the early 2000s, the global deployment of solar photovoltaics has been unprecedented. At the end of 2015, 222 gigawatts was the installed capacity globally. By 2050, this number is predicted to reach 4,500 gigawatts. With the predicted rise in global installations, there will also be a rise in the scale of decommissioned solar PV. Current Australian PV recycling is not economically feasible due to low influx of PV waste. Hence, more research on innovative recycling process is necessary. In our research, the main focus is on FRELP recycling process. According to the data analyzed from Australian PV Institute, Australia's cumulative solar PV installations reached almost 14 gigawatts by the end of 2019 and is expected to continue to increase their contribution towards Australia's energy demand. Cumulative solar PV installations in Australia since April 2001 depicts an exponential relationship. This relationship in the amount of installations is due to significant expansion since the end of 2009. Once the installations reach their end of life, the expected cumulative waste would follow a similar trend. Hence, Australia is set to experience serious challenges with environmental concerns, waste policy, and economics of sustainable PV waste management.
The reference system used in this research is all the installed crystalline silicon PV modules from April 2001 to September 2019 across several states in Australia, and an average solar installation of 1900 kilowatt hours per meter square is calculated. After the end of life, the modules are assumed to be landfilled or recycled using baseline and FRELP process for energy and material recovery. Another important characteristic of this system is its material composition. In our case, it's the crystalline silicon, which is predominantly made of glass, aluminum, and non-recyclable materials such as polymers. The assumptions are the module's power rating is 250 kilowatts with an area of 1.7 meters square, and only the module is considered, excluding mountings, cables, and other systems.
The FRELP method aims to achieve 100% recycling of the PV modules. The method is divided into 4 stages: recovery of aluminum and connectors through basic disassembly of the panels, recovery of EVA and glass through infrared process, recovery of energy and ash from the sandwich, and extraction of silicon through acid leaching and filtration, recovery of silicon and other materials through further electrolysis and neutralization process.
To calculate the amount of secondary materials, which can be used as primary raw materials, also known as secondary raw materials in a circular economy, two different recycling processes are considered. One is the baseline process where silicon and silver is not recycled, and FELP process where all the materials are recycled. Although FELP has high recycling rate, it uses strong acids and alkaline liquids to recover silicon and extract silver. The effects of these wastes are relatively unknown, hence proper management has to be developed. The carbon emissions in recycling are mainly due to the incineration of polymers. The series in blue presents the carbon emissions in recycling. If the modules are not recycled and sent to landfill, the emissions represent in gray. However, if the recycling is done using FREL process, the total carbon emissions that can be saved are depicted in orange. The potential value involved in future of recycling in Australia is calculated using the value per panel per element in the module derived from a certain research. The net profit that can be generated over the years based on the expected PV waste is plotted on the figure in the left, and the total value that can be generated is around 424 million, out of which 63 million would be the profit, although this doesn't consider the capital investments and operating costs of this industry. It still describes that the future of PV recycling could be economically feasible.
Limitations of this research are that it only considers crystalline silicon photovoltaics. The economic benefits are not calculated in depth, rather computed through suitable data from other researchers. The amount of energy involved in recycling is mostly unknown. Harmful effects of landfilling PV waste are not considered.
Highlighting the importance of circular economy, energy payback time for a multi-crystalline PV module can be reduced by 35%. For a monocrystalline PV module, it can be reduced by 16%. As carbon emissions is a function of energy payback time, it follows the same trend. Hence, for a circular economy, the emissions are lower compared to non-circular economy. Based on the value created, the recycling of crystalline silicon PV modules may be economically feasible. Since significant amount of PV waste is not expected until the year 2038, the government has ample amount of time for waste management of PV modules after they reach the decommissioning phase.